All right, here's an explanation of Lab 20. So in Lab 20, we're going to be doing the opposite of what we just did in Lab 19. So in Lab 19, we had a circuit already pre-wired, and then we had to figure out what the count was. In Lab 20, we're going to be given the count, and then we're going to have to figure out how to make that happen, so how to wire the circuit. So there's a few things we need to know in advance. One is how the JK flip-flop works. So 0, 0 is no change. 0, 1 on J and K is reset, so Q is going to be equal to 0. J1, K0 is set, so Q is equal to 1. And 1 on 1 is toggle. Now for this, there's one more thing that we need to know before we can start, and it's based on what we're trying to do. So we're trying to get, if we know the count, we're trying to get the flip-flop to do a particular thing. So we either want the output of the flip-flop to change to a 0, or to change to a 1, or not to change. So we need to know what makes that happen. So, and I was going to say unfortunately, but there's two things that can make that happen. So for example, if your output is currently 0, and you want it to stay the same, or have the next output also be 0, there's two ways that you can make that happen. And again, this is all based on what we know of our flip-flops. So on J and K, to go from 0 to 0, that's either going to be no change, or it's going to be a reset. So if you look at those two conditions, essentially, as long as J is 0, it doesn't matter what K is, right? Because if J is 0, whether you no change or reset, the output's going to be 0 on the next one. So the way that we do that is, as long as J is 0, K is don't care. It doesn't matter what K is. Okay? So there's going to be one of these things for every state that we have. So if we go from a 0 to a 1, again, there's two things that can make that happen. We could toggle. That would make it happen, or a set would make it happen. So then essentially, it's kind of the same situation here, but in the opposite, right? As long as J is 1, it doesn't matter what K is, okay? So we're just going to rewrite that as long as J is 1, it doesn't matter what K is. Now, if your output is currently at a 1, and you want it to go to 0, well, two things there too. One is going to be toggle, and the other one is going to be reset, which is 0, 1. So in this particular instance, as long as K is 1, it doesn't matter what J is. So we're just going to rewrite this as long as K is 1, it doesn't matter what J is. And you may notice a pattern here, so you can pretty much guess that the other one's going to be X0, but let's talk it through anyways. If it's at 1 and you want the output to stay at 1, then you could either have no change, or you could have a set. So again, in this instance, as long as K is 0, it doesn't matter what J is. So I'm just going to do this. Sorry, X. Now, we need to know this because we're going to need to manipulate this on the flip-flops. So for example, if I have a count that goes from 2 to 7, well then in binary that would go from this to this. So the least significant bit here, QA, would need to go from a 0 to a 1. The B flip-flop would go from a 1 to a 1, and the C flip-flop would go from a 0 to a 1. So that will help us figure out what we need to put on the J's and the K's and how and why and where. So we're going to use Karnaugh maps for this. So again, let's start with our problem statement. When we had Lab 19, we had a circuit that was wired up, and we had to figure out, based on what was on the J's and the K's, what that counter would do. In this case, it's going to be the opposite. We're going to give you a count, and we're going to design a synchronous counter that's going to fulfill that count when we wire it up. So the first thing we need is the count. So let's say I want the counter to start at 0, and then I want it to go to 4, and then I want it to go to 1, and then I want it to go to 3, and then I want it to go to 5. And then back to 0. So again, this is a very arbitrary count. I'm just picking it out of the air. So we're going to go from 0 to 4 to 1 to 3 to 5, and then back to 0. And there's no reason why I'm picking this counter. This is just what I wanted to do. So we have to figure out now, if I have three JK flip-flops, how do I wire them to make sure that it does that, right? So we're going to need a few things. So the first thing we're going to need is Karnaugh maps. You're going to need a Karnaugh map for each J and K for each flip-flop. So we need 6 Karnaugh maps, unfortunately. So we're going to have So that's our Karnaugh maps drawn out. This is going to be for the C flip-flop, this is going to be for the B flip-flop, and this is going to be for the A flip-flop. Now the other thing we need is we need the count, and I'm just going to draw it out in binary because that will help us figure out what we're doing. So we're going to go 0, 0, 0, 1, 0, 0 for 4, 0, 0, 1 for 1, 0, 1, 1 for 3, and 1, 0, 1 for 5. Okay, and that's all we need, because there's 5 states. So, where do we start? You can do this 2 ways. You can fill out all of the C Karnaugh map, and then go to all of the B, and then do all of the A. Or you can do each individual state all the way across. Doesn't really matter how you do it. That's probably the way I'm going to do it. But again, it doesn't matter how you do it. So the trick here is we're going to, so again, what we're doing is we're designing a synchronous counter. We have a count, right? We have a state diagram, and we have the count here listed in binary. So this is QC. I always put the most significant bit on the left. Okay? And we're just going to identify the counts in the Karnaugh maps, and hopefully it will make sense. So the first thing we're going to do is start with state 0, 0, 0. Right? So state 0, 0, 0, if you look at the Karnaugh map, this is 0, 0, 0, so we're in this box. Okay? So for the first state, 0, 0, 0, we're going to be in the top left-hand corner of each box because they're all 0, 0, 0, 0, 0, 0, and so on. So we're going to look at, so again, what we're trying to do is we know that our first count is 0. We know that we want the next count to be 4. So we know that we need the C flip-flop to change from a 0 to a 1. We know we need the B and A flip-flops to go from a 0 to a 0. So again, this is either going to be toggle or set, which we determined here, right? We're going from a 0 to a 1. So toggle or set, so as long as J is 1, it doesn't matter what K is. And that's exactly what we're going to put in our Karnaugh maps. So if C is going from 0 to 1, we go to our table, we see 0 to 1, right? Because that's what we want our flip-flop to do, our C flip-flop. We want to go from 0 to 1. And we know that from 0 to 1, J has to be 1, and it doesn't matter what K is. So again, because we're at count 0, 0, 0, we're going to go to the 0, 0, 0 box. So this is the J and the K, J and the K, J and the K. So if we go from 0 to 1, 0 to 1, J has to be 1, and it doesn't matter what K is. So J has to be 1 in the 0, 0, 0 box, and it doesn't matter what K is. For B, we need to go from a 0 to a 0. 0 to a 0, J has to be 0, and it doesn't matter what K is. So I'm going to stick with this 0, 0, 0 box. And for the B flip-flop, I'm going to enter 0x. And the A does exactly the same thing as the B, so it's going to be 0x. So again, our first state was 0, 0, 0. So we're aiming for the 0, 0 box in the Karnaugh map. And we know that if I'm going from a 0 to a 1, J has to be 1, and it doesn't matter what K is. If I'm going from a 0 to a 0, J has to be 0, and it doesn't matter what K is. And again, same thing for here. So this one's now done. So now we're going to look at the 1, 0, 0 is the next count. So 1, 0, 0 is this box right here, the lower left-hand corner, right? 1, 0, 0. So now we're looking at this state. So when we're at count 4, the 1 has to go from a 1 to a 0, right? So C, the output, has to go from a 1 to a 0. A 1 to a 0, it doesn't matter what J is as long as K is 1. So again, 1, 0, 0 is in this lower left-hand side. And if I'm going from a 1 to a 0, from a 1 to a 0, in this lower left-hand side, 1 to a 0 is x1, so it doesn't matter what J is, as long as K is 1. The B flip-flop is going from a 0 to a 0, so that's 0x, again, still in the 1, 0, 0 box. And the A flip-flop goes from a 0 to a 1, so that's 1x. So now this one's done. Our next count is 0, 0, 1, so that's the top right-hand box in each Karnaugh map. So the C flip-flop goes from a 0 to a 0, so that's 0x. The B flip-flop goes from a 0 to a 1, so that's 1x, again in the 0, 0, 1 box because that's the count I'm on. And the A flip-flop goes from a 1 to a 1, so that's x and 0. So now this one's done. So 0, 1, 1 we go 0, 1, 1, so that's this box in the Karnaugh map. So the C flip-flop goes from a 0 to a 1, so that's 1x, and I'm entering it in the 0, 1, 1 box because that's the count we're on, and 0 to 1 is 1x, so the j is 1 and the k is x, so that's why I did the j is 1 and the k is x. The B flip-flop goes from a 1 to a 0, so that's x1. And the A flip-flop goes from a 1 to a 1 to the next count, so that's x0. And that one's done. So now we go to the 1, 0, 1 box, and that's in the bottom right-hand corner. So now we're going back to 0. So the C flip-flop is going, going from a 1 to a 0. So 1 to 0 is x1. The B flip-flop is going from a 0 to a 0. That's 0x. And the A flip-flop is going from a 1 to a 0. 1 to a 0 is x1. So that will be x1. Again, we were in state 101, so I'm in the 101 box, and I put the j and the k based on this table. Now, the Karnaugh map accommodates 8 states. We only have 1, 2, 3, 4, 5 in our counter, so that means all the other ones are don't care states. So once you're finished with your counts, you can just pop in here and put X's in every one of the unused states. So now all you have to do is solve for the Karnaugh maps. So this is the C flip-flop, this is the J Karnaugh map, so this is going to be JC, this is going to be KC, this is going to be JB, this is going to be KB, and this is going to be JA, and this is going to be KA. And once we've solved those, we know what to wire to the individual J's and K's to make our counter do what we want it to do. So, solve this Karnaugh map. I'm going to have this here, which is QA naught, or this here, which is going to be QB. KC, I can actually make a loop of 8 here, so this is just going to be 1. JB, all I can do here is a loop of 2. So this is going to be QA and QC naught, I believe. QA and QC naught, correct. Again here I can make a loop of 8. This is easy, so that's just a 1. Here I can make a loop, I can't make a loop of 8, but I can make a loop of 4. So this is going to be simply QC. And KA looks like it's going to be the same thing actually. QC. Now, once we have that, we know exactly how to build our counter. So again, when I build this counter, I'm going to omit the presets and clears and clocks, just to make sure the diagram doesn't get too complicated. But this will be a synchronous counter, so all the clocks are clocked from the same source, and we can assume that all the presets and clears are high. So we're going to have 3 flip-flops. QB, 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 QB naught. And this is JC, QC, QC, QC naught. And now all you have to do is take what we did in the Karnaugh maps and just wire it up as we've determined here. So for example, JA and KA, they both hook up right to QC. So we're going to take QC and wire it up to both JA and KA. KB is going to be just simply 1. And JB is going to be an AND gate with QA and QC naught. So let's do that this way. QC naught. And JC is going to be an OR gate with QA naught or QB. I think now you can see why I didn't put the clocks and the presets and the clears. And KC is just going to be equal to 1. So now, if you were to build this circuit and start to clock it, it would count 0, 4, 1, 3, 5, 0, 4, 1, 3, 5, 0, 1, 3, 5, and so on, based on the wiring that we did here. And again, the process is, you know what the count is that you want. Lay it out in binary so you can see it a little better. Use Karnaugh maps to account for all the options for J's and K's as you go through. Solving the Karnaugh map gives you what to hook up to the J's and K's for all 3 flip-flops. And once you have that, you just draw the circuit, design it as, or just draw the, implement basically the design that you've got from solving the Karnaugh maps, and then you should be good to go.